Hey everybody, Lars here. This is going to be the first review video for Unit 4. We're actually halfway through. The summer is flying by. I do not know where this summer is going. We're going to do something a little bit different in this one, in that I've got to find time and do a bazillion different things this weekend. As you know, yesterday I was at Google. I took a bunch of pictures, and we're going to talk about a bunch of different cool data sciencey things on Tuesday when we have class. So I'll save all that for class. Meanwhile, I'm exhausted because I went there for a certain reason, and then it turned into something else. And then me and a buddy went down to the 911 memorial, and then we hopped on the path, went back to Newark, went to Iberia to have Rodizio, blah blah blah. I don't get home till like 11 o'clock, and I'm exhausted. And then I had to get up today and go on a 25-mile bike ride, which it's fun, but my God, it wasn't pleasant. So, and this coming week, I have to do a Python workshop on Wednesday. I have to do some other things. So I am going to save a little bit of time. And the way I'm going to save that time is that I shot this video last summer, in the summer of 2016. And for whatever reason these things happened, that video nailed it. That video does a really good job of going over things and discussing all the different topics and all the different things we're going to talk about. So what I did to save time last semester, because I just went back. Usually what I do is I go back and I look at all my past videos. I know all my past videos are online. I know that you know all my past videos are online. That's fine. You watch them as many times as you want. If people want to watch earlier videos, I'm like, why would I complain about that? That's fantastic. Watch as much as you want, as much as you need to understand what you're trying to learn and what you're trying to get out of it. Anyway, I go back and I look at my past videos to prepare to make this semester's videos, because I always make them fresh, because I want it to be topical, and I want to talk about things that we experience in class and the things that we are doing. And as I went back and I looked at the one from the summer of 2016 a while back, I'm like, wow, that really nailed it. I don't know if I'm going to hit on all those points and say all those correct things and boom, 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 boom. So last semester, I just, becoming a more sophisticated Camtasia user, I went and I grabbed that snippet out and I used that snippet. So I'm going to do it again. I'm speaking to you now, obviously, and then you're going to get a clip from about a year ago when I ran over sorting, and somebody's car alarm is going on. When I went over sorting and searching in Big O last summer. So, and while I don't think I do it, if I refer to different things, I may refer to the fact that it's a summer class, but that's actually apropos for us, so that's not really an issue. But just so you know, you're going to see me. The beard's a little bit longer. I have a buzz cut. And it's a year ago, so I will have, it's just before I pop my Achilles tendon. You don't care about that, though. So I'm going to give you that video. Then afterwards, I'm just going to say, hi, I'm back. But you know what? Wait a day or two. I'll get you the recursion video, which I'll probably shoot fresh, and then we'll do announcements then. But as far as announcements are concerned, the two big things are Tuesday night, the midterm is due. Tuesday, we have class number 3. And it's going to be a good class, so make sure you're there. We're going to discuss the final project, okay? We're getting close. We're at the halfway point. So we're going to discuss the final project. We're going to go over the Harshad assignment, and I'm going to show you how I do the Harshad assignment. And we're going to talk about Google, because there's a couple different things that occurred when I was visiting Googly Google in the city yesterday that made me think of our class and made me think of data science and made me think of a whole bunch of different things. So we're going to review all that stuff, all right? So without further ado, let's go back and let's go in the time machine to a year ago, and you can see what I look like with a buzz cut. My hair's too long right now. I'm actually hiding it by wearing this baseball hat. I need a buzz cut. I need to go do that. Maybe I'll do that Monday morning. So anyway, you're going to get that video, and then when it's over, I'll pop back for maybe a minute or so, and then we'll be done. All right? All right, then without further ado, let's go into the time machine and go back 1 year. Here we go. Hey everybody, Lars here. We are going to do the first review video for Unit 4. And as I usually tell the story, when I teach Python, it's a little bit different than when you get an introduction to computer science course when you first go to a university. If you first go to a university like Rutgers or anything else to become a computer science student, you will take a class called Introduction to Computer Science. Not Intro to Programming and not Programming, but Intro to Computer Science. And what we do is two different things. One is we get you started and begin teaching you the first language we're going to use. Here at Rutgers, we use Java. When I was a kid a long time ago and I did my degree, it was Pascal. Now at a lot of top universities, people are starting to use Python. But what happens is as you go through the course, you don't just go through what we're going through, looking at data and the representation of data, then looking at sequences and how to organize our data, then looking at iteration and how to navigate our data. They do that, but they also sprinkle in computer science concepts along the way. And what I do when I teach this course is I think to learn just how to program, sometimes those computer science concepts can get in the way a little bit. So what I do is I extract them, and I go through the process of teaching you how to program, teaching you how to take, logical thoughts and codify them and put them in code and solve problems that way. But I do think those computer science concepts and the different things we do there are important, because at the end of the day, computer science is about seeing how we solve problems with computers, how we solve problems in algorithmic discrete steps where we have a problem state and we start with an initial state and we work step by step to a goal state. So Unit 4 is where you've got the Python under your belt already. Okay, you know the basics of computer programming with Python. Now it's less learning Python and more using Python. So now that you have all of that under your belt, I'm going to reintroduce these computer science topics in this unit. They are simply sorting, searching, what we call Big O, which is really just the examination of the efficiency of your algorithms, and you'll see it's easy and I'm not going to kill you with it. And then we look at recursion. Later, as you'll see, we're also going to look at loading a third-party library and doing some graphs with it. And then, at the very end of the unit, I do some exception handling and some things with dictionaries. The exception handling and the dictionary, I'm not going to kill you. You're probably not going to see that on a quiz. But like I always say, I want you to be aware of it. I want you to be exposed to it. Because exception handling, being able to handle when things go wrong while your program is running, is pretty important. And if you program in any professional capacity, you have to do that. It's just the way we create professional code. You have to think of all the things that can go wrong, and you have to handle those situations. And that's all exception handling is. Dictionaries are very important. It's a data structure that is used in Python all of the time, but because, and I'm going to tell you this story when we start talking about sorting, I've only got 11 weeks to teach you Python. So I've got to make decisions on what we concentrate on, what we do, what we don't do. One of the things I really don't sit on and go over is dictionaries as a data structure. But I want you to see it, so I put it in the slides. Boom, boom, boom. All right. Let's get started. Let's run through what we're going to run through today. The first video, I'm just going to go through basically the first half of the slides. I'm going to go through sorting. We're going to talk about searching, and then we're going to talk about Big O at the end of it, because it kind of tells a linear little story. Let's go. I think I have the slides set up here. If you have a chance, go read about the supercomputer. We're ranked number 2 in the Big Ten as far as our supercomputer is concerned. That is us. Today, the first day of the unit, and this is where I want to be, the sorting hat. The story is this. When you first go to university to become a computer science student, you basically do some of the things you guys have been doing. You learn about the representation of data, integers, floating point, boom, boom, boom. You learn about simple lists. When I was a kid, they were just called arrays. You learn about for loops and iterating and things along those lines. But then, if you take your class in the fall, like I did when I was a kid, around the beginning of October, you are introduced to sorting. And sorting is not necessarily difficult, but there's a whole bunch of different ways to sort data, be it numerical, be it alphanumerical. And for the next couple of weeks, sorts and sorting are the bane of your existence. And because you're young and you don't know what you're doing yet, you wonder, why in God's name am I sitting here bothering with all of these crazy sorts? Bubble sort, quick sort, J sort, merge sort. Why do I care about all of these sorts? When you get older and you get further on in your computer science program, or you turn into an old fuddy-duddy like me and you work at a university, you realize that that is the way that we introduce the efficiency and the examination of algorithms to young students, because the different sorts have different efficiencies. Some are terribly inefficient, like a thing called a bubble sort. You'll see the bubble sort. And some of them are very efficient, like a merge sort and things along those lines. That is what early computer science educators in the 80s were trying to get across to us. They were trying to show us, look, this is the way we solve problems. Some of them are efficient, some of them aren't efficient. You need to have your eyes on that stuff. So we'll talk about that. Like I said before, I'm teaching Python, and I got to do it, especially in this summer session, in only 11 weeks, so I got to make decisions. And one of those decisions I make early on is I'm not going to have you code up a sort. Usually we would go over the chapter, and I think they do a merge sort in Zell. They may even do a bubble sort, although we rarely do bubble sorts anymore. They really are terribly inefficient. But they're easy to code up, so we want people to code them up and use them and you know, sort their own data along those lines. Basically, sorting is just putting things in order, alphanumeric order, numeric order from high to low, from low to high. Basically, what every sort does is compares numbers, and if they need to be in a different order, switches them. And some sorts will break things down into different groups and sort the groups and then put all the groups together. Some things will grab an item and compare it to everything in the list up and down the line. There's a whole bunch of different ways to do sorts. And what I do is I give you the URL to sortingalgorithms.com, where you can go and watch these sorts run and see all the different kinds of sorts: insertion sort, bubble sort, merge sort, quick sort. They are all there. And they'll even show you them in pseudocode, so you can see how they work and what they're doing. All right? You don't have to code up any of the sorts. If you want to, that's fine. There's a couple of ways to do it in Zell in the chapters I give you, but I'm not expecting you to code up a sort and know the algorithm for these different sorts right off the top of your head. As you can see, Python has a built-in method on lists so that you can sort your list anytime you want. And Python uses a thing called the TIM sort. Now, a lot of these sorts have been around since the 50s or 60s. It's funny, the TIM sort has only been around since the early 2000s. So if you want to, go to Wikipedia and read about that. I've always found that very interesting. But as you can see, it's almost like in your statistics class, the first time you see hypothesis testing, or the first time you see confidence intervals, or the first time you see linear regression, you do it by hand. And you're like, oh, this is crazy, this is nuts. But after you do it by hand once and you understand it, then the professor will say, okay, from now on, let the computer do it. Let SPSS do it. Let R do it. It's kind of that way with sorting, too. In computer science, we make students code up a couple of different sorts so they understand the inner workings. And then when they're done, we say, all right, you'll never have to do that again. We're skipping that part. I'm not going to make you code them up. We're going to jump right to the answer, which is, ta-da, using a sort method. So as you can see, I have a list and I print it and it's all out of order, and then I just run the sort method on it down here and I reprint it, and boom, from -2 all the way up to 99, it is sorted. Okay, we can also do it with alphanumerics, with strings. So if you give it a mixed up list and then you tell it to sort, it will sort in alphabetical order if it sees things like that. Okay. One last thing we're going to talk about with sorts is, you know, our magic about lists is that we can have mixed data types in there. I can have strings with integers, with floats, with a whole bunch of different things. But what happens when I try to sort that list and I mix up integers with strings and a whole bunch of other things? And what happens is, you get an error. Because, you know, they always say you can't compare apples and oranges. It's true. You can't compare apples and oranges. So Tim sort when it gets Lars in 33 and Johannes in 52, and you can see the Mets are in there. It doesn't know what to do with it. Now, later in your computer travels, you might learn Java, and you might learn about something called sortable, and you might learn about something called comparable, and you might learn that you can teach these programming languages how to sort different things like that. But out of the box, Python's like, I don't know what to do with this. I can't do it. And as you can see, if you read that error on the bottom, it says unorderable types, because it doesn't have the first clue how to compare an integer and a string, because we didn't tell it how. Okay, so be wary of that when you want to sort things with built-in sort functions. Usually they have to be of the same type, so that it's very simple to know what's greater than something else and what's less than something else, and so far along those lines. Okay, now we start out with sorting when we go into computer science, because sorting is very important. We care about sorting, and the reason, and this is good because it gets into some data science-y stuff, we care about sorting because when we first start examining data and getting ready to solve a problem, we want to know as much about our data as possible. Okay? Because if we know certain things about our data, then we can choose certain time-tested algorithms that can find answers for us. If I know my data is sorted, it gives me an incredible advantage when it comes to searching through that data for a particular item. So sorting becomes important, and you're going to discover how important in a second, because we are going to look now at searching. Let's say you have a list of 1 million numbers, and they're not sorted. They're all jumbled together. And I come up to you and I say, hey, can you please write me a computer program that determines whether the number 7 is in that list of numbers you have. So, how are you going to solve that problem? You've got an unsorted list. You don't know anything about your data. All you know is that you've got a list with 1 million numbers in it. Frankly, you have no choice except to, what we call, go to war on it, or basically look at every single number in that list to see if there's a 7. So you'll start at 0, not a 7, okay, go to the next one. Not a 7, go to the next one. And so on and so on and so on. And if that 7 resides in the last spot on the list, that's the worst case scenario. You will have had to have looked at every item in that list. So, you know, in stats and computer science, we use the letter N to denote population or the size of a list or something like that. Whatever N is, whatever the size of your list is, in this case 1 million, that is how many potential lookups. Whenever you look to see if a number is a certain thing, we call it a lookup. That's how many lookups you would have in a worst case scenario in what we call a linear search. If I've got unsorted data, I have no choice but to do a linear search. I got to look at everything because I don't know. It could be here, it could be. I have no idea. I have no idea what's going on. So if I've got 500 things, worst case scenario, linear search is N 500. I have to look 500 times. If I've got 1 million, I've got to look 1 million times. Think about big data. Think about some of the data sets Google has, or some of the data sets that they're keeping on customer data in Amazon, stuff like that. A linear search just isn't going to cut the mustard. That's too much data to go through, okay? So, is there a way I can search through data more efficiently and not have to look at every single item to figure things out? It turns out there is, but there's a trick. You need your data to be sorted. And if your data is sorted and you know that it's sorted, then you can do what we call a binary search. Now, a binary search is interesting and fun. Take my same list of 1 million numbers, and this time I'm going to tell you the list is sorted. And I'm going to tell you, does 7 appear? I'll stick with the same number, though it's going to be easy. Does 7 appear in this list? Well, what can I do if my number is sorted? My data is sorted. I can play high-low. I go to the middle of the list. If I have a list of 1 million items, I know the middle is 500,000. I go to the 500,000th item, and I look at it, and I say, is this equal to 7? And the algorithm says no. So then I ask a second question. I go, okay, is this number higher or lower than 7? And then the algorithm comes back to me and says, this number is higher than 7. What does that tell me? If the middle number of this sorted list is higher than 7, what do I then know? Instantly, I know that my number will not appear in the upper half of that list. So I throw it away. I don't need it. I know my number's not in there. Okay? Instantly, I've gone from 1 million to 500,000. I've cut it in half. So now what do? I repeat the process. I now go to the 250th item and I say, hey, are you 7? And the algorithm says no. So then I say, okay, are you higher or are you lower than 7? And the algorithm comes back to me and says, you know what? I'm higher than 7. I can do it again. I can then get rid of the top half of my list. So now in just 2 lookups, just 2, I've taken 750,000 items out. And I don't have to look at them and I don't have to bother with them. And I can keep going in this fashion until I either find the 7 or I realize there's no 7 in the list. Okay? If this were a linear search, I would have to do 1 million lookups to determine that the number 7 does not appear in my list. But in a binary search scenario where every time I do a lookup, I can cut my list in half, I only need 20 lookups. Think about that. If I know my data is sorted, I can do a binary search. And if I can do a binary search, instead of 1 million lookups, I'm down to 20. That's incredibly efficient. And then when we're done talking about searching, we're going to talk about Big O analysis. And we're going to see binary search is incredibly efficient. So if I have sorted data, I can now start doing sort things to show you. Here I just do it with 16 items and I show you. Big list, cut it in half, cut it in half, cut it in half. Only 5 lookups, I can find something in 16. Okay? It's instead of having to look at 16, I only have to look at 5. That doesn't sound so fantastic, but if you take the example of 1 million and compare it to 20, that's huge. You're going to see it's log n. It's the opposite of exponentiation. We'll get into that when we talk about Big O. Right now, I want to show you the code. And I'm going to show you, actually, I have 1,000. I have 1 million down there. I create a list of 1 million numbers. And then I search for the worst case scenario, 999,999. And then we'll take a look at how it goes, because if I'm not mistaken, I have coded it up for us. I call this blsearch.py. B for binary, L for linear, because I am a good egg, and I also coded up a linear search down there. We are going to compare the two. But this is the code right here for a binary search, okay? I get it. It looks complicated at first glance. Trust me, it's not. Please, trace through it. Look at what it's doing and how it's doing it. You will find that when you look at this, all it is doing is taking a list, going to the middle of the list, seeing if a number is what I'm looking for. If it is not, then I cut the list in half. Okay? That's all I'm doing. And I do it with indexes. I have a number called mid, and mid is set here. It's low plus high divided by 2 with integer division, because I'm doing an index. I don't want any floating points. And middle is always the middle of my list. So if it's 1 million long, middle is going to be 500,000. If it's 500,000 long, middle is going to be 250,000. And I keep looking at the middle for the item, and then I ask, is it higher or is it lower? See? Well, I ask lower here, and then I use an else, because if it's not equal to and it's not, lower, then it has to be higher. So read this code, go through this code. For now, I'm going to show you that I have 2 functions here. One is called bsearch. It takes what I'm looking for and a list. And I also have lsearch, which is a linear search, which takes the number I'm looking for and a list. And linear search is just, it goes through a loop and looks for it, blah, 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 blah. So what I do here is I create a list. I use range to create a list from 1 to 1 million. And I put it in a list called mynums. Then I give the binary search the worst case scenario for a list of 1 million numbers. Okay, and then I print it. Then down here for linear search, I just give it a random number. It's pretty big though, because we're gonna look at it real quick, and then we're gonna compare it to binary. Let's run this bad boy and see what we get. All right, I set up my binary search so that it prints out a lot of data as it runs, so that you can see it running. So you can see here I have a step counter. I tell you what the mid is. A step counter. I tell you what the mid is. So you're gonna be able to see the binary search work. And the step counter is 1, 2, 3. That's how many lookups I'm doing. Every time I do a lookup, I print out what I'm looking for, and then I print out what the mid is, what I'm looking for, all the way up to 19. Okay? And when I get to 19 and the mid is 999999, I got it. I say the number is found. Boom. Okay? So that 19 is how many lookups I needed. Okay? Now, if it wasn't in the list, then I would look up one more time and I'd get 20. So that's the max on a list of 1 million numbers. That's incredible, to be able to search 1 million numbers with only 20 lookups. But that's what binary search gives you. That's what sorted data gives you. Now, my linear search, I looked and, hey, I found the number. Of course I found the number. It's an ordered list from 0 all the way up to 9999. But look how many times I had to look. Okay, because we start with 0, it's one more than the actual item I was looking for. Now, if I do this, and I change this to look for 99999, in the linear search, I'm going to look for the same thing I did in the binary search. And even though it ran pretty quick, it's because it's a computer. If we did this with billions, you would definitely see the difference in efficiency. In only 19 lookups, I found my number. The linear search said, oh, it said number not found. Why did it say number not found? Interesting. Did I do something wrong? What if I gave it an 8? Yes, okay. My linear search somehow jumps out before it gets to the very end. Because now, in that many passes, I found my number. Okay, I'll have to look at that. Don't you love it when things explode in the middle of videos? So, in 19 lookups in a binary search, I find my number. Here, I have to look 999,998 times. Okay? Think about the efficiency. Think about the savings there. I mean, it's incredible. Okay? And it's because we have sorted data. And it's because we know with a binary search we can play high-low and literally throw out half of the list every time we do a lookup because we know our number is not going to be up there. Okay? This code right here, blsearch.py, I'm going to put up in Sakai. And you're going to see with your second homework assignment, I want you to have a binary search and a linear search in a library that you use. You're going to read some random numbers, clean them up, and then you're going to, use different searches on them. Use this code. I have no problem with it. I want you to read it. I want you to understand it. But at the end of the day, if you use this code when you create your library with your binary search and your linear search, I got no problems with it. Check out my linear search though, because apparently something was going wrong with it. I return. Well, I know why I return a -1 if I don't find a number. But why I wasn't finding 99999, I don't know. So I'm going to have to look at that algorithm. But I'm going to give you this code. Okay? So you don't have to code up all that craziness. You have it. But I want you to read through it, and I want you to understand it. Because you'll see when I ask you the question and I give you the homework assignment, you're going to see, how things work, and you're going to want to know the inner workings. And you'll see it's not hard. You'll have this code when you get that. Okay? So that is binary search, and as you can tell, that's what sorting gets you. As you can see here, I used that code when I created these slides. And here I talk about coding up the linear search so you can compare the two. We did that. This is the YouTube video where I'm talking about there, so you're getting all that done. Binary versus linear, the efficiency is insane, and we're about to look at that now. Here I think I do another example and another example. But here is where we start talking about the third topic we're going to discuss in this video, and that is what's called Big O. Now, first time I heard Big O, I thought about this guy, because I was a basketball player when I was a kid, and Big O is the nickname of Oscar Robertson, who played basketball for Cincinnati and was a big basketball star in the 60s. There's also Big O, the character in anime. So when people hear Big O, they probably don't think about what we're going to talk about. Big O is notation used by computer programmers when we examine the efficiency of algorithms. The O basically stands for order of magnitude. So it's like order. And we call it Big O because when we do order of magnitude, we care about big things. We don't care about little things. So if the efficiency is expressed like in a polynomial, we only care about the biggest exponent. If it's x to the fourth plus blah, 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 all we care about is x to the fourth. Okay? We care about big things. And there are common efficiencies for different kinds of algorithms in computer science. And what we do is we examine how efficient our algorithms are by thinking of the Big O number. Now, this probably sounds confusing and kooky, but basically the simple ones that you have to think about are Big O of 1 is constant. So if I print my name, Lars, and no matter what the algorithm sees or no matter what it does, I'm just going to print Lars, well, it's the same result every single time. So it's constant. It's Big O of 1. When I have a task that maps to the size of my data, like we did with a linear search, then Big O is N. So if my list is 1,000,000, then N is 1,000,000, then that's what the Big O is. It's N. It's whatever my data size is. Because in an unsorted list, I've got to look, I potentially, worst case scenario, have to look at all of the data. We always look at the worst case scenario because we don't want to get bit in the rear end when we do efficiencies. Some people will say, well, can't you just, do the average? Do the. No, you can't. Because the minute you start planning on the average won't happen. Murphy's Law exists, believe me, and it is very strong when it comes to computer science. So we always, when we look at efficiencies and algorithms, look at worst case scenarios, okay? So a Big O for a linear search is whatever the size of the data is, or N. The binary search is different. Here, I believe I went to Wikipedia and stole a graph to show you some Big O complexity numbers. A binary search has Big O of log N. And if you remember your math classes when you were in school, I don't know when you get logs. Do they even do logs anymore? Logarithms are basically the inverse of exponentiation. So where exponentiation gets big, and you can actually see some on that graph, log is the other direction. It gets small. You can see here it's red. It's right here very close to the actual number itself. You can see O of N, which is a linear search, maps 1 to 1. These dimensions are weird, but you see that's 100, that's 100, boom, right there. So if it were 70, it would be 70. 50 would be 50. O of log N is super efficient, so it's super low. So if you had 100 elements to search through, it's incredibly small, the number of lookups that you would need. Because think about it, for 100, you'd go 50, 25, 13 down the line. It would be like 5 or 6. Okay, so that's how efficient the binary search is. The Big O for a binary search is log N. Now then we can get some bigger ones. We can get like N log N, which is like, I don't know, merge sort. That's for a lot of things that get divided up and then put back together. Then we start getting into the big boys. Then you get N to the second. Then you get 2 to the N. And finally, every computer programmer's nightmare is N factorial. Okay? Look at that. You can see how these efficiencies rocket off the screen. Those are problems which are what we call intractable, where if we had all the time in the universe and all the space in the universe, we still wouldn't be able to attack these problems because they get huge fast. There's a very famous problem called the traveling salesman problem. If you look it up, it's traveling salesman problem, or TSP. And you can see basically all it is I'm a traveling salesman. I've got to go to 5 different cities, find me the shortest route. That's it. That's the problem, basically, simply put. Problem is, once you get greater than 12, 13 cities, you're running into problems because you literally have to look at every single route, and it's 13, 14 factorial. It's 13 times 12 times 11 times 10 times 9. That's how many routes there are. And pretty soon that number gets monstrous. I mean monstrous. I mean so big you can't. I mean, I think if you go factorial 22, 23, I forget what the number is, you all of a sudden are more items than there are stars in the universe. It gets insane. It gets crazy fast, real fast. Some of those problems are interesting, and the way we tackle them is not with algorithms, because algorithms can always find you the solution. We deal with heuristics. We deal with things that'll get us close, that'll approximate what we think. And there are some decent heuristics and approximations for the traveling salesman problem, but still, it's pretty huge. If you want $1 million, go to the Clay Mathematical Institute and study up the P versus NP problem. That's pretty much what you're dealing with when you're dealing with big O of and factorial. Those are the kind of problems, and I'm not going to get into polynomial versus non-deterministic polynomial, but those are the kind of that's like the biggest problem in computer science. But I digress once again. I don't want you to think, oh my God, I haven't done logarithms in a while. Oh my God, I don't want to deal with factorial 22, factorial blah, 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 blah. You won't have to. Again, I want you exposed to this. I want you to see it. I want you to understand that your linear search is O of n. So it goes up as the number of data items goes up. I want you to understand that a binary search is O of log n. So it's very efficient, very, very small, even for big numbers. I mean, it's only 20 lookups for a data set of 1 million items. Okay? So I don't want you to worry about big O. I want you to see it. I want you to feel it. I want you to understand that when we have algorithms, we do examine them to see how efficient they are, and we have ways of, saying, oh, this one has big N of n log n, so we can understand the efficiency is going to be this. It should take this long to run on this much data, blah, blah, blah. We want to be able to do that, and this is how we do it with big O complexity. Okay? All right. Then that, if I'm not mistaken, and I have some other rather technical looking things here. Oh, okay, and I talk about P versus NP in the slides. And then we get to the break. Okay? I'm saving recursion for the next time we meet. Well, the next time we meet on YouTube. All right. So there you have it. Sorting, searching, and big O. Steep in that for a couple of days. Tomorrow, maybe tomorrow, I have to go to a picnic. I have to get ready for this workshop. It's for little kids. I'll tell you about it on Tuesday. And I have to do some other stuff. But I want to get to the recursion video because, as you know, I always want to make sure that you have all of your resources for at least a week before the assignments are due. And the assignments are going to be due a week from tomorrow because the unit is going to end on Sunday. It's not crazy, though. You'll be fine. I don't want you to get, scared and think you don't have enough time and this and that. It'll be fine. The assignments are really no great shakes for this unit. This unit, and I'll tell you this when we're in class, this unit is kind of a break in between Unit 3 and Unit 5 because Unit 5 is another big boy. In a regular semester, Unit 5 is 3 weeks, and that's where we're going to cover object orientation, but I don't want to get ahead of myself. So you be good. Please make class on Tuesday. It's going to be a good one. Any questions, put them in the forums. Tuesday's important. All will be explained about the final project. We'll go over deadlines and things along those lines. We'll have a little fun, learning about Google, maybe get some discussion going, talking about some different data science topics. It's going to be a good one, all right? Then you be good. I'm getting out of here, but I'll be in touch via announcements. You know me. You know how I roll. So you'll be talking to me in the next couple of days, all right? All right, you be good. Have a good night. All right, bye.